This is the screencast for section 2.5, example 5, finding complex zeros. So we start off this problem the same. They give you a polynomial, and this time they give you a complex number, 1 minus 2i. Well, that's the only zero I know, so I have to put that through synthetic division, and I can put that through synthetic division. What, Miss Larson, you're crazy. No, I can't. Yes, I can. Okay, here we go. Drop the 4. 4 times 1 minus 2i is 4 minus 8i. 0 plus 4 minus 8i is 4 minus 8i. Now off to the side, you will multiply 1 minus 2i times 4 minus 8i, and then write, I'm just kidding. Go to your calculators and go to mode. Make sure you are on A plus BI mode. So arrow all the way down to real, arrow to the right, and hit enter. Now you can actually take 1 minus 2i and multiply by 4 minus 8i in your calculator. How nice. That does not mean you do not need to know how to do that by hand. So 1 minus 2i is second decimal place times 4 minus 8 second decimal place, or I, and I get negative 12 minus 16i. And I can add 17 to that. That gets me 5 minus 16i. Now I have to multiply by 1 minus 2i. Hit enter. And I've got negative 27 minus 26i. So now I add 14. And I get negative 13, what was that? Minus 26i, duh. 14 minus 27 is negative 13 minus 26i. Multiply that by 1 minus 2i. And if 1 minus 2i is in fact 0, which the problem told me it is, so I know it is, hopefully this will equal 65, which seems kind of magical at this point. But in fact it does equal negative 65. 65 minus 65 is 0. Since the remainder is 0, I can see that 1 minus 2i is a 0 of the function, which means x minus 1 minus 2i is a factor. Now, if you start writing down the breakdown of this factorization, you're going to have a really horrible thing to write. So I'm going to say that you do not have to write down every single factorization when you're factoring imaginaries or using imaginaries in synthetic division. Instead, you can write every other one. Now, remember, complex conjugates, or excuse me, imaginary zeros always exist in complex conjugates. So if 1 minus 2i is a 0, 1 plus 2i is also a 0. And we said that that imaginary zeros exist in complex conjugates because those complex conjugates, after they get multiplied out, the I terms go away. So as we put 1 plus 2i through synthetic division, you should see this bottom line get a lot cleaner. Okay, so I drop down the 4. 4 times 1 plus 2i is 4 plus 8i. You just distribute the 4. 4 plus 4 is 8. Negative 8i plus 8i is 0. Matter of fact, it's almost more tedious to use my calculator on this step, so I'm going to do this by hand. If I distribute the 8, I get 8 plus 16i, so 8 times 1 and then plus 8 times 2i. And then I add 5 plus 8 is 13, negative 16i plus 16i is 0. Don't need to worry about that. Now again, I distribute the 13, so I get 13, plus 26i. This time I get 0 all around, which is good because that means that 1 plus 2i is also a 0. Now I can start to write down my factorization. I did 3 different steps. I broke into 3 different pieces because I did 2 different synthetic division steps. X minus 1 minus 2i. X minus 1 plus 2i. Proved that was a 0. And then after all that was done, I got, 13 is the constant, 8 is the x, and then 4 is the x squared. So 4x squared plus 8x plus 13. Well, I can use quadratic formula on that. So now that I've gone through the quadratic formula, I can start to write out my linear factorization. So I have y equals x, I'm distributing the negative sign in this first one, so minus 1 plus 2i. Then I got another one, x minus 1 minus 2i. Then this last part I just broke up into two different pieces. So that is x minus the first 0, which is negative 1 plus 3 halves I. And then x minus negative 1 minus 3 halves I. So again, I'm going to distribute the negative. And we can't leave fractions inside of the parentheses in our factorization. So I'm going to factor out again a 1/2. So I'm going to get rid of the denominator in each of those parts. So y equals x minus 1 stays the same, plus 2i. X minus 1 minus 2i. Now I'm going to pull out or factor out or divide by 1/2. So x divided by 1/2 is the same thing as x times 2. So 2x. 1/2 divided by, or 1 divided by 1/2 is the same thing as 1 times 2, so that's 2. Now the 1/2 got factored out, so this got multiplied by 2, so the 2's would cancel, so this is minus 3i. And then the same thing goes for this second piece. I have 2x plus 2 plus 3i. So my factorization is 1/4, the two 1/2s in front, times x minus 1 plus 2i times x minus 1 minus 2i times 2x plus 2 minus 3i times 2x plus 2 plus 3i. Whew. So that is my linear factorization. And then the remaining zeros are what I have to identify. Since it's just asking for the remaining zeros, which is a little bit weird, those are 1 plus 2i, and then the other two that I found, negative 1 plus 3 halves I, and negative 1 minus 3 halves I. So now when I graph this equation, all of the zeros are imaginary. It will never cross the x-axis, and that is very possible because this is an even degree polynomial, so both of its end behaviors will be face up, and it just will never touch or cross the x-axis. The now try problem for example 5 is number 33. Using the given zero, one of them, find all of the zeros and write a linear factorization of f of x. So I know that 1 plus I is a 0, which means 1 minus I is also a 0. It's complex conjugate. So I'll put 1 plus I, and I'll write out all of the first terms and put this through synthetic division. So by using synthetic division, I found that 1 plus I and 1 minus I are definitely zeros, and I can start to break down my f of x. F of x equals x to the 4th minus 2x cubed minus x squared plus 6x minus 6 is how I started the function. Now I broke down using two layers of synthetic division into f of x equals, one of the zeros is 1 plus I, so that's x minus 1 plus I. The other one is 1 minus I, so it's x minus 1 minus I. And then what was left over was x squared minus 3. I don't need to use quadratic formula on that one. I can just set that equal to 0. So now my final factorization is f of x equals, I'm going to distribute the negative as I go here, x minus 1 minus I, x minus 1, and then plus I. And then the last two zeros I found are square root 3 and negative square root 3. So that's x minus square root 3 and x minus negative square root 3, which is just x plus square root 3. So when I graph this function, I will see that the x-axis will get crossed through at both positive square root 3 and negative square root 3. And my calculator can find those numbers, but they will not be exact. So we have to find the exact zeros, so you can't just say what decimal point your calculator spat out. You have to go through synthetic division and find the exact value. So we've got our linear factorization, and then it says find all of the zeros. So the zeros are 1 plus I, 1 minus I, square root 3, and negative square root 3. 4 zeros for a fourth degree polynomial.